All right, welcome to Learning Target 15B, Take 15. We're going to talk about being able to calculate the activation energy of a reaction using Arrhenius' equation. So hopefully we'll get through this without any interruptions. Okay, so we're going to look at the Arrhenius equation here. There are two versions. Here's version number 1, which is going to give us the rate constant in terms of an exponential function. And in this particular case, K is your rate constant. A is, according to this, the pre-exponential factor, but we've got another name for that, and I'll talk about that in a moment. E is your exponential, and it's raised to the negative activation energy, E sub A, divided by the universal gas constant times the temperature in kelvins. If I take the natural log of that equation on both sides, I will end up linearizing the equation into the form of y equals mx plus b. And so if I take the natural log of both sides, I'll have the natural log of the rate constant equals the negative activation energy divided by the universal gas constant times temperature in kelvins, plus my natural log of my pre-exponential factor, which I'll talk more about in just a moment. For the Arrhenius equations, we're going to assume that the reactants are in a gaseous state, and we're not going to delve into how this equation was derived. That's beyond the scope of IB chemistry. And in fact, if you were taking the exam, you could just look up the equation in the back of the data booklet. No need to memorize it. But since we're assuming that all the reactants are gases, we're talking about learning target number 1, where we were using the ideal gas law, and R for that equation is 8.314 or 8.31 pascals liters per mole kelvins. So in my little slide here, A is called the pre-exponential factor, but in IB, we actually call this the frequency factor. And the frequency factor takes into account, doing a lot of calculus, the proportion of particles that have the correct energy and orientation to have a reaction occur. Remember, with collision theory, you have to have particles collide, you have to have particles collide with the correct amount of kinetic energy, and those particles have to be in the correct orientation. If those three things don't exist, a reaction doesn't occur. So A takes into all of those accounts of collision theory. Don't worry about how we derive A. Just know that that's what that factor means. And the factor will be different dependent upon what chemical reaction we're talking about. So hopefully you paused the video back one slide, took some notes on the Arrhenius equation, both the exponential version and the linear version. And we're going to look at some graphs now. The first graph is going to be the relationship of the rate constant versus temperature in kelvins. And as we saw, the reaction or the equation is exponential. So it makes a lot of sense. As temperature increases, the rate constant will increase exponentially. And that makes sense because if I increase the temperature, I increase the number of collisions that can occur because I increase the amount of kinetic energy in each of the reactant particles. However, this particular graph is really not useful to find the activation energy, which the whole intention of learning about the Arrhenius equation is to calculate the activation energy of a particular reaction. So let's look at the linear version that's much more useful. So here is our linear equation, typical equation y equals mx plus b. Here is the natural log version of the Arrhenius equation, which will be put into this linear form, where y is going to be the natural log of k. The slope is going to be the activation energy divided by the universal gas constant. Your x variable is going to be the reciprocal of temperature in kelvins. And your y-intercept is going to be the natural log of your frequency factor. And I'm going to fix my little typo here. My little typo is right here. This should be a negative slope. As you will see in the graph. So in the graph here, we plot the natural log of k on the y-axis, the inverse of the temperature in kelvins on the x-axis, and my slope will be the negative activation energy divided by the universal gas constant. This enables us, solving for this little equation here, to calculate activation energy, which is really useful to figure out how much energy needs to be present in order for a reaction to happen. So this is great if you can always graph in order to find activation energy. However, sometimes you won't be able to graph because you won't know the frequency factor. If you don't have the ability to graph, we can solve for the activation energy if I know two rate constants with two corresponding temperatures. So I can find the rate constant at two different temperatures, subtract those two equations, and I will be able to find the activation energy. All right, so we are going to subtract these two equations in order to create an equation that allows us to solve for activation energy. So what I'm going to do here is I'm going to subtract the left-hand sides of these equations, and I'm going to take K2 away from K1, the natural log of both, and then I'm going to subtract the right-hand sides of the equations, putting the expressions in parentheses. Minus a negative T2 plus natural log of A. Get my mug out of there. Okay, so now what I'm going to see is I can cancel out my frequency factor on the right-hand side of the equation because I have the natural log of A minus natural log of A. So that's why it's really nice to subtract these two equations to get activation energy, because we don't need the frequency factor. I can also remember from maybe pre-calculus, some algebra class that you might have been in, that when I'm subtracting two natural logs from each other, what's happening is I can divide one of the constants by the other and take the natural log of the answer for that. And then I can clean up this left-hand side here. And I can see here that this turns into a plus. Now I can see that there's a common factor in both of these expressions that contains activation energy and the universal gas constant. So I can factor that out. And that'll leave me with the reciprocal of the first temperature negative plus the reciprocal of the second temperature. And then just to clean this up a bit, so I'm just doing a subtraction instead of adding to a negative value. One minus T2 minus 1 over T1. And there is the expression that will allow us to solve for activation energy if I know two rate constants and their corresponding temperatures in kelvins. And here we have that spelled out again. I would take a moment and jot down this equation. Have it in your notebook, define your variables, because this is what you're going to be using for the whole entire 15B learning target. Let's take a look at a practice problem that is going to enable you to solve for activation energy. And then we're going to do two more problems, one for you to be able to calculate the frequency factor and another one to calculate a new rate constant with a new temperature. So the values for the rate constant of a second order reaction at 25 and 37 degrees Celsius are 4,260 liters per mole seconds and 18,200 liters per mole seconds, respectively. Deduce the following values for this reaction to 2 sig figs. We are going to take a break from sig figs and not go through and make sure we have the correct amount of sig figs in every step. We've graduated from that because you're done with the IA. And we're also not going to practice some poor algebra skills when we're solving these problems. So here we're going to calculate the activation energy, and I'm going to do exactly the opposite of what I've been telling you for the last 3 years. I am going to plug in values to particular parts of this equation first before I actually solve. So the first thing I'm going to do is I'm going to remember that I've got to change my degrees Celsius to Kelvins. And so to do that, I add 273. And so I'm going to have a temperature of 298 here, and I'm going to have a temperature of 310 here. I'm going to plug that directly into my reciprocal of my temperatures. 1 divided 298. And I am going to have you trust me that when I solve that out, I get 1.30 times 10 to the negative fourth. And the units here, and I'm going to be really liberal about the units as well, but I'm just going to tell you it's 1 over Kelvins because it's the reciprocal of the temperature. Now what I'm going to go ahead and do is I'm going to solve out this natural log of the rate constants. So that's going to be the K1 over the K2. So I'm going to have 4,260 divided by the 18,200. I divide that first, then find the natural log. So make sure you do what's in the parentheses first and then get the natural log for that. And just to let you know, the units for that cancel out and I will get a constant of negative 1.45. So now I know a number that goes into the left side of the equation here. I know a value that goes into the reciprocal difference of the temperatures here. And now I'm ready to solve for the activation energy. So I'm going to say negative 1.45 equals EA, that's what I'm solving for, divided by the universal gas constant times 1.30 times 10 to the negative fourth. I'm going to divide both sides by 1.30 times 10 to the negative fourth. And then what I'm going to do here is I'm going to remember that R is 8.31, universal gas constant. And I'm going to multiply both sides by 8.31. So when that happens, since this is in the denominator here, the 8.31s cancel out. Since my 1.30 times 10 to the negative fourth is the numerator and denominator, it cancels out, and I have now isolated my activation energy. So when I go ahead and put this into my calculator, I'm going to get a value for activation energy that is going to end up being in joules. And that's because 8.31 is a number that measures energy in terms of joules. So I'm going to put that into my calculator. And I also forgot to put this negative sign over here with the reciprocal of the temperature. So I put a negative sign here as well. You can solve that out by hand to see that it is negative. And in joules, with 2 sig figs, I get 93,000 joules. They're asking for it in kilojoules per mole. This is a molar value, so all I've got to do is move the decimal 3 places over to the left, and I'll get 93 kilojoules for my answer. So we got to remember that value because we are going to need to use it to get the frequency factor, which is the next practice problem here. Okay, so to get the frequency factor, I'm going to use the exponential version of the Arrhenius equation. Does not matter which one you use, you should come up with the same answer, whether it's the exponential version or the natural log version. I just like the exponential version for this. So remember, the exponential version is going to be rate constant equals frequency factor e to the negative EA RT. And I can use any particular temperature I want for this that I was given on the previous slide. So I'm going to use that temperature of 298, which had a corresponding K value of 4,260. So in order to get my frequency factor, I'm going to isolate A. I'm going to divide both sides by the exponential function negative EA divided by RT. So I guess I'm doing a good job following my rules of isolating my variables first. So this piece goes away. And now I'm going to have a function here that's going to enable me to solve for my frequency factor. So I'm going to have 4,260 all divided by E to the negative, and I've got to make sure it's the joules version of activation energy, 93,000 divided by 8.31 times the 298. So order of operations here, I'm going to solve the denominator first and then divide it into the numerator. So this turns into 4,260 divided by 4.9 times 10 to the negative 17th. And then when I do this last bit of division here, I am going to find that I get 8.7 times 10 to the 19th, positive 19th. Now, really easy trick with units for A. It's going to have the same units as your rate constant. And since this was telling you is a first or a second order equation, I found that the units are going to be liters per moles. I don't need that because I already used a division sign, moles seconds. So that's going to give me my A value. And I am going to now use all that information in the exponential version of the Arrhenius equation to get my new rate constant at 50 degrees Celsius. Immediately change that over to Kelvins by adding 273. And when I do that, I get 323. And I'm going to have K equaling A exponential minus EA RT. And I just fill in all the information that I've got. This one's going to contain a lot of scientific notation. So you're going to have to really watch order of operations and make sure you've got your scientific notation in parentheses. And then this is going to be negative 93,000 divided by 8.31 times 298. Order of operations here, I'm going to solve for the exponential first and then multiply it by the frequency factor. And so when all of that is going to be said and done, I am going to find my new rate constant for 50 degrees Celsius to be 7.8 times 10 to the fourth, same units as my frequency factor and of all of the other rate constants on the previous screen, moles per second. So we did three things here. We found the activation energy using two different temperatures. We found the frequency factor using the exponential version of the Arrhenius equation. And last, we found a new rate constant for a new temperature, which you should know that a good double check is to make sure if the temperature continues to increase, your rate constant should continue to increase. Which it did, because when I raised another 10 degrees, I ended up getting a new rate constant of 7.8 times 10 to the fourth. So hopefully that will be helpful for unit learning target 15B. You will see an attached set of practice problems that go along with this. And thank you for hanging with me with this. Have a great day.